Welcome to Understanding the Threats and Attacks on Data Science Applications. I want to start with a special thanks to Man Singh, who's an expert in data streaming and data engineering, and Kunal Patel, who's an expert in machine learning and security, for their help and input related to understanding data science and data streaming applications better. So what I'm talking about today is one of the biggest blind spots and holes in most security programs across the enterprise. And what I have up here is a picture of prototypical data science application where enterprises are looking to make better decisions and get better insights into how their business runs and how they interact with customers by collecting a lot of data about their customers, their processes, their systems, feeding it into some type of aggregating bus or messaging queue like Kafka, and then processing that information via different tools like Spark or Flink, and loading that data into other databases that can be used for analytics or decision-making or customer insights. And almost every company is undertaking this type of data science application. I was in Halal Brothers the other day, and I looked and noticed when I did a search on their data science openings, they actually have a data science program and are looking for people in data science. So you wouldn't imagine how prevalent this undertaking is within organizations. The other thing I noticed is when I talk to a lot of my security friends, you don't ever hear about them even looking at these components or understanding how these components work. And today, I'm going to give you an introduction and an understanding of what those threats are so that you can go back to your organizations and identify these threats and make your organization or enterprise more secure. So the thing about these data science applications that makes them a little bit more concerning is that they make decisions in aggregate. So any vulnerabilities that you have in these applications are going to inherently affect more users and possibly affect your company. So when we talk about attacking a data science application and its attack surface, the first thing that typically is looked at are its algorithms through its training data, or attacking the algorithms through its training data. The next thing is the infrastructure of that data science application. So the Kafka, Spark, Flink, Airflow, Kubernetes infrastructure components that make up the data science application. The data science engineers are also part of the attack surface because they have access to the sensitive data and large amounts of data. We also have developer tools that the data scientists use that provide an attack surface for the bad guys. And then finally, we have the data cleansing and preparation logic that as application security engineers, we're so familiar with in terms of finding application security vulnerabilities. So let's talk a little bit about attacking an algorithm's data. So in the past, I've been talking about attacking machine learning models through data poisoning. And you see a lot of papers talking about turning fishes into dogs and dogs into fishes, or getting the classification of the model to take a picture of a dog and turn it into a fish, or vice versa. But when you look about that, really, when we're talking about attacking an algorithm's data, it's more than just pictures. So when you think about the realistic ability of an attacker to insert data into your training data directly, it's probably not that high a probability. But when you look at the picture down at the right, and you look at the inputs to the system, which are on the left, what two areas do you see that would be prime targets to insert your poison data? If you look at these data sources, that would be one, right? The sensors, the information that's mined from the web logs, if you can get to the server file system that has the files that are read by the data ingestion engine, like Kafka, then you can modify there. The other place you can insert data is directly into the data ingestion engine if it's not secured properly. So let's talk about some examples of this, because when you think about it, it seems kind of, impossible. But there are actual cases where there was a stock trading program, which basically was an algorithmic-based automated programming or automated buy and sell stock trading algorithm, which was looking for patterns in behavior. And what the other stock trading algorithm, which was trying to fool it, would basically submit thousands of buy or sell orders and then cancel them within a millisecond. And what would happen is that those algorithms that looked for a lot of quick buy and sell orders would then put in their orders, and the system that was fooling them would cancel them and then trick the other system into basically behaving in the way they wanted. And if you look at another stock trading algorithm, basically it was trying to look at tweets or postings on different financial websites within a defined period. And if they did sentiment analysis, where they basically identified the stock name and if the posting was positive or negative, and if there were a lot of them in a short period of time, it would trigger the buying or selling of stock by these automated algorithms. And so actually there were people manufacturing these stories and tweets with bots, and that would trigger the algorithm. The other thing that I think is possible and that may be occurring even to this day, but is not talked about, is how cyber espionage can be used to basically mess with the sensors and information that your system is using in real-time decision-making processes. Imagine a manufacturing plant where someone's hacked their network and goes in and is now creating false sensor information. And if you look at manufacturing systems, they're very similar to robotics and autonomous vehicle in that everything is published and subscribed because they want everything loosely coupled. And so you're dealing with a lot of the same components that are in data science applications, namely messaging buses like Kafka, which then allow different manufacturing parts to be loosely coupled and introduced and pulled out and replaced pretty easily versus trying to integrate specific component protocols and connection mechanisms. And so this whole Kafka thing is going to be around and is going to get bigger and going to be more important in your enterprises as you move forward because of its ability to provide loosely coupled information to systems across the enterprise that need it and share information. So when we look at now attacking the data science infrastructure, you think about all these different tools that are used in data science applications: Kafka, Spark, Flink, Airflow, Kubernetes. And Spark is probably one of the most popular data science tools out there. And in their security documentation, literally the first paragraph before anything is talked about in their Spark security documentation, it says security in Spark is off by default. This could mean you are vulnerable to attack by default. Spark supports multiple deployment types, and each one supports different levels of security. Not all deployment types will be secure in all environments, and none are secure by default. Be sure to evaluate your environment, what Spark supports, and take the appropriate measures to secure your Spark deployment. Now, I don't know about you, but I think that is a kind of big disclaimer. And so as security professionals, when you read something like this, you need to be prepared, because essentially Spark is saying, hey, if you use our stuff, it's all on you. And you better take notice to secure this stuff, because we admit we're not securing this stuff by default, and you need to take the appropriate steps. So if you're using Spark or any of these other things, you need to look at the security of those different data science applications, because this statement means it's all on you. So when we look at securing data science infrastructure, you have to look at all of the components in that infrastructure. You have to look at how the managers and the executors and the drivers communicate, what role each component plays in each of these different tools, how they communicate, how they authenticate to each other. And it's so important to look at these internal components. You can't just say, oh, I've got Kafka and it's secure. You need to understand how the components work together, how they authenticate to each other, and how do they communicate. If you're dealing with data, a lot of times there may be sensitive data in the data that's being processed. So you need to make sure that the data in motion is going to be secured. And then you need to also think about how these components connect to internal data sources. So the source components will pull data from possibly sensitive data sources, and the sync components will possibly write to sensitive data source. So you need to understand how they're going to connect to these data stores. If your components are cloud-based, how are they protected from third parties? What type of security measures are you using for your Kinesis or Kafka in the cloud? And how are they protected? What are your security groups? How are they configured? And then you have to look at what data you're passing around, and if there's sensitive data in that, and then asking yourself, why? Because ideally, you want to scrub the data of all the sensitive data. And if you pass around sensitive data, then you're creating a nightmare for governance, because once you put data on the bus, any other systems that need it or want it can get it. And where does that sensitive data flow, and how is it protected? So you've got to understand what other systems are using that data and how they're protecting that sensitive data. And do they even have permission to access and use the data for the specified purpose? When you look at GDPR and other privacy regulation, consent is a very important thing. And finally, you want to understand how your secrets and credentials are managed by the infrastructure components. So they're going to connect to sensitive data stores. They're going to have to authenticate. So how do you manage those credentials that are used by the components to connect and authenticate to those different stores. The third attack surface for data science applications are the data science engineers themselves. I went to LinkedIn and I basically searched for data science Amazon, and you can get a lot of information off there and learn about who in the organization is basically the data scientists. And the data scientists have access to reams of data. So consider this scenario. Oh, what in your data scientist got pwned? Oh no, the data lake with 100 million user records was exfiltrated from their machine. So attackers no longer need to break into the back end of your DMZ and the firewall and avoid the IDS and IPS. They just need to compromise a data analyst machine. The other thing that data scientists do is when they get the data that they need to work on, they may put it on a S3 bucket to share with other members of their team. Well, if you don't lock down those S3 buckets, well, what happens when it's accessed by anonymous users? So you need to have some type of enforcement or security policy around your data scientists' use and sharing of data. And you have to understand if and when they're going to be taking data from the data lake to their local machines to work on locally. And if that data is further shared, where does it go? How is it managed? When is it deleted? The next area that typically is an attack surface for data science applications are the tools themselves. So Jupyter is a very popular tool. And basically what it does, it allows you to execute code written in your browser on a server machine. And it could be your own machine, but it provides a nice environment to make things easier for data scientists to set up everything and write their code and document it and put it in a format that can be easily shared. Now, listen to those words that I said. Execute code written in your browser on a server machine. Basically, this has turned remote code execution from a bug into a feature. So the problem that you see mostly is that data science will set up their Jupyter servers, don't have the time or inclination to set up the valid certificate signing requests and go through the red tape of requesting an SSL certificate from internal processes to set up appropriate domain name. And so what happens is that if developers are not using SSL, then an attacker who's on the network can easily sniff the credentials going back and forth if they're using username and password and get into that machine. If they're reusing their credentials, then basically they can use those credentials to log into other network resources. The other thing is, since we're here talking about application security, a common practice among these Jupyter notebooks and the models is to use pickle load or joblib.load to serialize or deserialize the models or the data associated with the notebooks. And if an attacker can basically write to these files, they can insert commands that can be executed in pickle when it's deserialized. And I provided a link there. This has been a known issue for a long time, and deserialization attacks are very important and a common, unfortunate security vulnerability that is very prevalent. So finally, we're going to look at attacking the data cleansing and preparation logic. So you have a situation where you've got this data, it's got to be cleansed, it's got to be pulled in, it's got to be cleansed, it's got to be enriched, and then it's got to be pushed on to different systems that want that data. And typically you're looking at three high-level components. You're looking at sources, processing components, and sinks. And these are chained together to create a pipeline. Now let's talk about sources. So basically sources are components that pull data from databases, files, messaging queues, S3 buckets, and they can be batch or stream-based. Batch typically means you have a file and you're loading that file and processing it. Stream-based is where basically you're receiving events from some source, some sensors, web logs, etc., and you're processing them in real time. Now let me ask you, which do you think has more vulnerabilities? Well, of the two models, it typically happens that the streaming-based applications have more vulnerabilities because the source of the untrusted data is closer to a potential attacker. So an attacker is not going to have the data file extract to modify and insert their payloads into. However, an attacker can basically insert their attack payloads into the web application logs through their usage of the application, or user feedback, or looking at the URLs that are being sent to the backend systems for their app usage, or the IoT sensor values that are being sent. And so the sources are the location where typically the streams of input from a messaging infrastructure are typically converted into objects to be passed to processing components. So you want to be really careful about looking for deserialization vulnerabilities in these components. And the sources, once they convert these objects, the streams into objects, they'll pass them down to processing components that they are connected to as a part of the pipeline. So let's talk about processing components. They receive data from sources and process or enrich the data. So what does it mean to enrich the data? Basically, you're taking data from other systems and you're trying to add more data to the existing data. And then when you do this, you're using the data that you received in the objects. And so basically what you have are the normal application security vulnerabilities in these components, the SQL injection, the file path manipulation, all that is going to be found in here. Because this is where kind of the bulk of the business logic for how data cleansing and enrichment occurs. And it's going to be connecting to all these different systems. It could also make other calls to REST applications, so you have server-side request forgery possibilities. So you're going to look for those vulnerabilities there. Sinks are basically what receive the objects from the processing and cleansing logic. And then basically the sinks are going to push these objects to other messaging queues, databases, or the data and the objects to other databases, files, S3 buckets, for other downstream applications to process and utilize in their systems. Again, here you're going to look for your standard application security vulnerabilities in the top 10 from OWASP. So when you're building these applications or these pipelines, you've heard it before millions of times, validate your inputs. So what you find with a lot of these data processing applications are that because they're getting data from what they think are inherently trustworthy sources, they tend to kind of, forget about really looking at their data carefully And you'll have good data engineers that do that and want to make sure that, you know, the values are coming across correctly and the, you know, in the correct format. So let's go dive deeper into the input problems related to streaming apps. And they kind of fall into 5 areas. Looking at valid values, identifying duplicates when types are mixed, filter bypass issue, mismatched character sets, differing storage or field types, and knowing all of your potential uses. So let's go into detail on this. When we talk about the valid values, you're basically ensuring that your data is bounded. So if your application receives an age field, is the value appropriate? So what do you think would be some invalid age values? Well, if you got a negative value, there's no one with a negative or 0 age. So that's one example of something that we'd want to look for. So the other thing is there's this concept of windowing within these pipelines where they're going to look for duplicates. And the way that they look for duplicates and throw those out is by specifying certain fields in the input fields as primary keys for deduplication purposes. However, there are problems that occur when a data engineer assumes that the primary key field is a certain type, but it is represented as a different type. So in this case, you know, the data engineer is assuming that the field is a number, but it's represented as string. So one way to get around the deduplication logic within a window is if you look at the bottom here, we have 2 records. Normally, the second record should be discarded as a duplicate, but the attacker in the primary key field, which is the first column, used 001. So the filtering logic basically said, oh, this is not a duplicate. However, when this row gets converted into an object, this is going to be converted over to a number, and then it's going to override the original one. So we also have filter bypass issues. So, you know, what you're going to see is that you have different processing components that can be chained together and reused, and they're going to make certain assumptions about the rules or constraints on their data. And when you have differing rules or constraints between components in a chain, you're going to find security vulnerabilities. You see this often in HTTP request smuggling or cache poisoning or these, you know, HTTP parameter pollution. Basically, you've got a chain of components operating on the data, and they have different assumptions or rules or constraints that they're working with. And so this mismatch is when basically you can get around certain filters, right? So we also have character set issues. So in today's environments, enterprises are global, and these architectures are going to share data with other systems in other parts of the world because they're going to be aggregating this information or disseminating this information, and they're going to be making decisions based on the data that's received and processed. And so what you're going to find is that most people don't think about character sets. They install the operating system, they set the default character set to whatever it is that they're in their locale, and they install the software. And so what you can have is that these applications inherit the default character set of the operating system that they're installed in. And then when data is processed and converted into and out of their character sets, it can allow for certain dangerous characters to be to be put in where a benign character was in that character set, and then allow the other consuming application to get the dangerous character. And there's a bunch of, you can Google this, there's a bunch of different research and speakers who talked about character set security issues. So the other thing is differing storage or field types. And so, you have one system that expects integers to be 64-bit and another system that only supports 32-bit integers. Well, integer overflows, here we come. And finally, we have knowing all of your potential data uses. So, look at that picture again. We have input coming in, going into these messaging queues that is then sent to different components for processing, enrichment, stored in different databases. And then that data could be sent to another messaging queue, which could be sent to other apps, which is processed, which those apps send to another messaging queue, which then sends to other apps. And when you look at the complexity of the data and how it's being used and where it's being used, it's easy to quickly lose track of where this data is used and how it's used. And so when you try to input filter for your application, if you're in the beginning part of this process, well, it's going to be difficult for you to input validate for all of the potential uses downstream because you won't know, because new apps are going to be added to these message buses that are going to do new things that you haven't even thought about. And so, when the data crosses these different application and operating system boundaries, any assumptions you made about the original use of the data are lost and new unforeseen uses arise. And so you need to make sure that every one of your downstream components are defensive in how they input validate their data and make no assumptions about the cleanliness or the veracity of that data that it receives. It needs to still be very vigilant and validate its input to its use. So thank you for listening. That's the talk for today. If you have any questions, I'm opening it up. This is my contact if you have questions. Thank you for listening and being a part of this today. I hope it helps you.